There is a place on this planet where the ground has not seen sunlight for millions of years. Not because the sun does not reach it, but because something else arrived first and never left. Ice, in quantities difficult to hold in the mind, settled over an entire continent and pressed downward with such patience, such indifferent weight, that the land beneath it simply disappeared from human knowledge. Not destroyed, not gone, just hidden. So thoroughly and for so long that most people alive today have never once considered what might be lying underneath. And perhaps that is the strangest part of the story. Not what Antarctica conceals, but how rarely anyone asks. Tonight, let that question sit with you for a moment. There is no hurry. Wherever you are right now, whatever time it is in your corner of the world, this is a place where curiosity is allowed to move slowly. The lights can be low, the noise can be far away. If you're lying in bed, let the pillow take the weight. If you're driving, let the road unspool gently. This is not a lecture. It is not a lesson. It is a slow walk through something ancient, something buried, something that has been waiting with more patience than any living thing has ever shown. So before you let yourself settle completely into that comfort, take a moment to like the video and subscribe, but only if what you find here feels worth returning to, and if you would share where you are listening from tonight and what time it is there. Not the time on the clock, but the time as your body feels it. That small detail connects this moment to every other moment someone else has spent listening in the dark, wondering about the same questions. Now consider what we think we know about Earth's past. The story of this planet has been read for the most part from places that cooperate with curiosity. Mountain ranges where layers of rock sit exposed like the spines of open books. River valleys where erosion does the work of turning pages. Deserts where ancient surfaces lie bare under open sky, waiting for anyone patient enough to look. These are the places that gave us geological time, fossil records, climate histories. They offered their secrets because conditions allowed it, because wind and water and the slow collapse of stone created openings. But there is an entire continent that offers none of these conveniences. An entire chapter of Earth's history that remains, for all practical purposes, unread. Antarctica covers roughly 14 million square kilometres. It is larger than Europe. It holds 90% of the world's ice and about 70% of its fresh water. In places, that ice rises more than 4 kilometres above the bedrock beneath it. The weight is so immense that the continent itself has been pushed downward, deformed by the burden it carries. Beneath that surface, hidden from every satellite photograph and every aerial survey, lies a landscape as varied and dramatic as any on Earth. Mountain ranges taller than the Alps, valleys deeper than the Grand Canyon, river channels carved by water that no longer flows, lakes sealed in darkness for spans of time that make human civilization feel like a brief flicker. And yet when most people picture Antarctica, they see white, flat, featureless, empty, a place defined by what it lacks rather than what it holds. That perception is not accidental. It is a consequence of the ice itself, which acts simultaneously as a barrier and a preservative. It hides everything beneath it while protecting it from the forces that would normally destroy geological records. Rain does not fall on bedrock sealed under kilometres of ice. Roots do not crack stone. Rivers do not carve new channels. The processes that constantly rewrite the surfaces of other continents have been suspended here, frozen in place by conditions that arrived tens of millions of years ago and never fully retreated. This makes Antarctica both the most frustrating and the most tantalizing place on the planet for anyone trying to understand Earth's deep past. Frustrating because access is extraordinarily difficult. Drilling through kilometers of ice requires years of planning, specialized equipment, and budgets that few institutions can sustain. Tantalizing because what lies beneath may be better preserved than equivalent records anywhere else. The very conditions that make the continent hostile to human presence also make it ideal for long-term preservation. It is a vault. sealed not by design but by circumstance, containing records that were written when the world looked nothing like it does today. There was a time when Antarctica was not frozen. That sentence alone can feel strange, almost impossible, because the image of a white continent at the bottom of the world is so deeply embedded in how we understand the planet that alternatives seem like fantasy. But geology does not care about human intuition. The rocks beneath Antarctica formed under conditions that had nothing to do with ice. They formed when this land was connected to other continents, positioned differently on the globe, bathed in climates that supported forests and rivers and complex ecosystems. Fossils pulled from the edges of the continent confirm this. Leaves pressed into stone, wood turned to mineral, pollen grains trapped in sediment for tens of millions of years. These are not speculations. They are physical objects, recovered from places where ice has retreated just enough to reveal what was there before. The question is not whether Antarctica was once different. The evidence is clear that it was. The question is how much of that difference is still preserved beneath the ice, waiting for instruments sensitive enough to detect it, for drills patient enough to reach it, for minds willing to reconsider what they thought they already knew. Because if Antarctica holds records from periods that are poorly documented elsewhere, if it captured transitions and extinctions and climate shifts that were overwritten on other continents, then what lies beneath that ice is not just geological curiosity. It is a missing chapter, not a footnote, not a frozen afterthought. A chapter torn from the book and placed on a shelf made of ice, where it has been resting quietly for longer than any human story, any written language, any memory we have ever tried to hold. And so the question that opens this evening is not dramatic. It does not demand an answer tonight. It asks only that you hold it gently, the way you might hold a stone found on a beach, turning it over in your hand, feeling its weight, wondering where it came from. What if the part of Earth's story we understand least is the part that has been best preserved, locked away beneath a continent that most of the world has agreed to ignore, not out of malice, but simply because the ice made it easy to look elsewhere? Long before the ice, long before the silence, the land that would become Antarctica occupied a very different position in the world. Not just geographically, but relationally. It was not isolated. It was not peripheral. It sat at the heart of a vast arrangement of continents that shared coastlines, climates, rivers, and life. To understand what Antarctica lost, it helps to understand what it once belonged to, because the story of its burial begins not with cold, but with connection. The name given to that ancient landmass is Gondwana, a term borrowed from a region in central India where geologists first identified rock formations that seemed impossibly linked to formations found thousands of kilometers away on entirely different continents. Gondwana was not a single uniform slab of land. It was an assembly, a slow collision of crustal plates that brought together what we now call Africa, South America, Australia, India, Madagascar, and Antarctica into a southern supercontinent that persisted for hundreds of millions of years. During that time, Antarctica was not at the edge. It was near the centre, connected by land bridges and shared geology to neighbours that today sit in tropical and temperate zones. This is where the dissonance begins. The continent we associate with absolute cold, with lifelessness, with the most extreme conditions on Earth, was once warm enough to support forests, not sparse patches of cold-resistant scrub clinging to survival at the margins. Dense, functioning ecosystems with canopy trees, understory plants, root systems that built soil, insects that pollinated flowers, and rivers that carried nutrients across landscapes that stretched unbroken into what is now South America and Australia. The evidence for this is not ambiguous, it is etched into stone. In the 19th century, a peculiar fossil plant began appearing in rock formations across the southern hemisphere. Glossopteris, a broad-leafed tree fern, was found in India, in southern Africa, in South America, in Australia, and eventually in Antarctica itself. The Austrian geologist Eduard Suess was among the first to recognize that these scattered occurrences could not be coincidental. The same species, preserved in the same geological layers, appearing on continents now separated by thousands of kilometers of ocean. Suess proposed that these land masses had once been joined, and he named the ancient southern continent Gondwana. Decades later, Alfred Wegener would draw on this same fossil evidence to argue for continental drift, an idea that was dismissed during his lifetime and vindicated long after his death. Glossopteris was not a simple plant. Its leaves suggest a deciduous habit, shedding foliage seasonally in response to changing light conditions. Growth rings found in fossilized wood from the same period indicate clear seasonal cycles, periods of rapid growth alternating with dormancy. This is significant because even when Antarctica was warmer, its position meant it still experienced extended polar darkness for part of the year. Life there had adapted. Trees grew vigorously during long summer days, storing enough energy to survive months without sunlight. The forests were not tropical, they were temperate, adapted to extremes of light rather than temperature, and they thrived for tens of millions of years. Beneath those forests, soils developed. Organic material accumulated. Rivers cut channels through the landscape, carrying sediment from highland to coast. These are not imagined details, they're recorded in the rock. Fossilized soils found in Antarctic outcrops show root traces, mineral weathering patterns, and organic carbon content consistent with forested environments. Sedimentary sequences reveal river deposits, floodplains, and lake beds. The picture that emerges is of a continent fully integrated into the living systems of the planet, exchanging species and energy with its neighbours across land bridges that have since vanished beneath the sea. What makes this history unsettling is not the fact that it happened, but the completeness with which it was erased from the surface. Other continents changed too. Forests came and went, climate shifted, but on those continents the evidence remained accessible. Layers of rock exposed by erosion told the story to anyone willing to read them. In Antarctica, the ice arrived before the story could be fully written into the accessible record. It sealed the landscape, pressed down on the evidence, and replaced a world of rivers and roots with a world of compression and silence. There is also the matter of what Gondwana's breakup meant for life. When continents are connected, species can migrate. Populations exchange genetic material. Ecosystems remain resilient because organisms can move in response to changing conditions. As Gondwana began to fragment, those pathways closed. Species that had once roamed freely across connected land masses found themselves stranded on pieces of crust that were drifting apart. Antarctica's biological communities, once part of a vast southern web of life, became increasingly isolated. And isolation, in evolutionary terms, is a sentence that can end in adaptation or extinction, depending on how much the world changes around the stranded population. The fossils that remain tell a story of narrowing. In older rocks, the diversity of plant species is high. Multiple families of trees, ferns, and flowering plants appear together. In younger rocks, diversity declines. Certain groups disappear, others become dominant for a time, suggesting that fewer species could tolerate the shifting conditions. This is not a sudden collapse. It is a long, slow diminishment, recorded in pollen grains and leaf impressions, that become rarer and simpler as the layers ascend toward the moment when ice replaced everything. What is haunting about this record is not the extinction itself, but the precision with which it was preserved. Other continents experienced similar losses, but subsequent life obscured the evidence. New forests grew over old ones. New species replaced those that vanished. The record was overwritten. In Antarctica, the ice arrived like a closing lid. It stopped the overwriting. It froze the last page in place. And because that page has been sealed for so long, it may contain details about the transition from a living world to a frozen one that simply do not exist anywhere else. The question that lingers is not whether Antarctica once supported life. The fossils have answered that. The question is what else was there, deeper beneath the ice, in layers that have never been reached, in sediments that have never been sampled. If the margins of the continent, the few exposed outcrops and coastal rocks, have already yielded forests and rivers and seasonal ecosystems, then what might the interior hold? A region so deeply buried that no human instrument has yet touched its bedrock in most places. Did the forests extend further than we know? Did ecosystems persist longer than current evidence suggests? Were there transitions recorded there, between climate states, between biological regimes, that would change how we understand the planet's deep past? The ice does not answer, it holds the question in place, pressing it down with the same patient weight it has applied for millions of years, and waits for someone to find a way through. A continent does not become isolated by choice. There is no moment of decision, no border drawn across the ocean, no wall erected against the warmth. What happened to Antarctica was slower than anything the human mind is built to feel. It was a drifting, a separation measured in centimetres per year, accumulating across spans of time so vast that the word gradual barely applies. And yet the consequences of that drifting were anything but gentle. They rewired the planet's climate, rerouted its oceans, and condemned an entire landmass to a kind of thermal exile from which it has never returned. The breakup of Gondwana did not happen all at once. It was a sequence, a series of fractures that unfolded over tens of millions of years, each one altering the geometry of the southern hemisphere in ways that compounded over time. Africa began to pull away first, opening the early Indian Ocean. India followed, tearing northward on a collision course with Asia that would eventually raise the Himalayas. Australia separated later, drifting northeast and leaving behind a widening gap that would become the Southern Ocean. But the separation that mattered most for Antarctica's fate was the one that came last, the opening of the Drake Passage between the Antarctic Peninsula and the southern tip of South America. That opening, which most evidence places somewhere around 34 million years ago, was not dramatic in the geological sense. It was a narrow gap at first, a shallow channel between two land masses that had been connected for hundreds of millions of years. But narrow gaps in the ocean are not minor details. They are switches. They redirect currents. They alter how heat moves across the planet. And this particular gap triggered a reorganization of ocean circulation that would transform Antarctica permanently. Before the Drake Passage opened, warm ocean currents from lower latitudes could still reach Antarctica's shores. Heat from the tropics was distributed southward, moderating temperatures, keeping the continent cool but not frozen, cold enough for seasonal variation but warm enough for forests, rain, and biological activity. The land bridge to South America acted like a valve, channeling water and warmth along predictable paths. When that valve broke, the ocean found a new route. Water began to flow uninterrupted around Antarctica, circling the continent in what would become the most powerful ocean current on Earth, the Antarctic Circumpolar Current. The significance of this current is difficult to overstate. It does not merely flow around Antarctica, it isolates it. By circling the continent without interruption, it creates a thermal barrier that prevents warmer waters from reaching the coast. Heat that once arrived from the north is now deflected eastward, cycling endlessly around the pole without delivering its energy to the land. The effect is like wrapping the continent in a cold blanket woven from moving water, a blanket that tightens with every revolution and admits nothing warm from outside. Once that circulation pattern established itself, a cascade of consequences followed. Temperatures dropped. Snow that had once melted seasonally began to persist through the summer. Ice formed at higher elevations first, in the mountains and on plateaus where air was coldest. Then it spread. Glaciers grew, merged and thickened. As white surfaces expanded, they reflected more sunlight back into space, reducing the amount of energy absorbed by the land. This albedo feedback, as it is called, is not subtle. It is a self-reinforcing loop. More ice leads to more reflection, which leads to more cooling, which leads to more ice. Once the loop begins, it is remarkably difficult to reverse. The forest that had endured polar darkness for millions of years could not endure the cold that followed. Trees adapted to seasonal light cycles found themselves facing temperatures that dropped below their physiological limits. Growing seasons shortened, rainfall patterns changed as atmospheric circulation adjusted to the new thermal regime. Species that had thrived began to retreat, first from the interior, then from the coast. Some migrated northward, crossing narrowing land bridges before they disappeared entirely. Others simply declined generation by generation until the last individuals vanished without witness. What is remarkable about this process is that it was not caused by a single catastrophic event. There was no asteroid, no supervolcano, no sudden rupture in the fabric of the world. The freezing of Antarctica was driven by geometry, by the slow rearrangement of land and ocean that altered how heat moved across the planet. The Drake Passage opened, the current formed, the feedback began, and over millions of years, a continent that had supported forests and rivers and complex life was transformed into the largest desert on Earth. A desert not of sand but of ice, where precipitation falls as snow and accumulates without end. There is something instructive in this. The forces that froze Antarctica were not exotic. They were the same forces that shape every coastline, every mountain range, every weather pattern on the planet. Plate tectonics, ocean circulation, atmospheric dynamics. These are not unusual processes. They are the ordinary machinery of a living planet. What made Antarctica's transformation extraordinary was not the mechanisms involved, but the way those mechanisms aligned, each amplifying the others until a threshold was crossed that could not easily be uncrossed. And here is where the story becomes relevant beyond geology. The same mechanisms are still operating, tectonic plates still move, ocean currents still respond to changes in temperature and salinity, ice still reflects sunlight, feedback loops still function. The difference is that the variables are shifting again, not because continents are drifting, but because atmospheric composition is changing at a rate that has no precedent in the ice core record. Antarctica's past shows how sensitive the climate system is to relatively small perturbations when they interact with the right feedbacks. The Drake Passage was not a massive geological event. It was a narrow opening, but it was enough. The isolation that followed did something else, something quieter and less often discussed. It preserved what was beneath the ice at the moment it formed. As glaciers advanced, they buried soils, river valleys, and forest floors. Organic material trapped under cold-based ice decomposed slowly or not at all. Sediment layers laid down in ancient lakes and shallow seas were sealed off from erosion, from biological activity, from all the forces that normally recycle the surface of the Earth. In this way, isolation became preservation. The same process that killed the forests also saved them, not as living systems, but as records, pressed into stone and sediment and frozen in place beneath kilometers of ice that has never fully retreated. The question that follows is almost too large to frame clearly. If Antarctica's isolation preserved its pre-glacial landscape more faithfully than any other continent's geological processes have preserved theirs, then what exactly is being preserved down there? And if the answer includes records of climate transitions, extinction events, and biological connections that were erased elsewhere, then the ice is not just hiding a landscape, it is hiding context, the kind of context that could reshape how we understand the planet's entire deep history. The Drake Passage opened, the current formed, the ice came, and the chapter was sealed. But sealed is not the same as lost. It is merely the same as waiting. The idea that forests once grew on a continent now buried under kilometers of ice can feel like something borrowed from fiction. It carries the texture of myth, of lost worlds invented to satisfy a longing for places that never existed. But the forests of Antarctica are not imagined. They left evidence behind, physical objects that can be held, measured, dated and studied under magnification. And the story those objects tell is not simple. It is a story of adaptation, endurance, and eventual disappearance so complete that only fragments remain, scattered along the edges of a continent that has made access to its interior nearly impossible. The first clues came from places where ice has not quite managed to cover everything. Along the Antarctic Peninsula, on Seymour Island, and in the Transantarctic Mountains, outcrops of rock pierce through the ice sheet like bones through skin. These exposures are rare, isolated, and often accessible only during brief windows of summer when temperatures rise just enough to allow fieldwork. But for the geologists and paleontologists who have reached them, the rewards have been extraordinary. Fossilized leaves pressed into mudstone, fragments of wood turned to mineral over tens of millions of years, pollen grains so well preserved that individual species can be identified under a microscope. Each of these objects is a message from a world that no longer exists on this continent, delivered through stone and time with startling clarity. Among the most significant of these discoveries are fossils of Nothofagus, the southern beech. This genus of trees is not extinct. It survives today in South America, Australia, and New Zealand, forming temperate forests that are among the most ancient continuous ecosystems on Earth. But its presence in Antarctic rocks tells a deeper story. Nothofagus fossils found on the continent date to periods when Antarctica was still connected to its neighbours, or had only recently separated. The trees grew in conditions that were cool but not frozen, enduring long polar winters without sunlight and surging into growth during extended summer days. Their wood shows growth rings, clear bands of seasonal variation that indicate periods of vigorous activity followed by dormancy. These were not struggling outliers at the edge of habitability. They were established forests rooted in soil, supported by rainfall, and integrated into functioning ecosystems. The growth rings themselves carry information beyond simple seasonality. Their width and density reflect the conditions of each growing season, how warm it was, how much moisture was available, how long the period of continuous light lasted. In some fossilized specimens, the rings are wide and evenly spaced, suggesting stable, favorable conditions sustained over many years. In others, the rings narrow and become irregular, hinting at stress, perhaps from cooling temperatures or shifting precipitation patterns. Read in sequence, these rings form a kind of diary, recording the slow deterioration of a world that was becoming less hospitable, generation by generation. In 2017, a discovery in the Transantarctic Mountains pushed the story even further back in time. Eric Gulbrandsen, a paleoecologist, and his team uncovered a fossil forest dating to approximately 280 million years ago, during the late Permian period. This was not a forest of flowering trees or southern beeches. It was older, stranger, composed of species related to seed ferns and early conifers that existed long before the familiar plant families of the modern world had evolved. These trees grew in a polar environment that experienced months of continuous darkness each year, yet they reached significant heights and formed dense stands. The preservation was remarkable. Some specimens retained cellular structure, detailed enough to study under high magnification, revealing how the wood grew, how nutrients were transported, and how the trees responded to their extreme environment. What makes this discovery particularly compelling is its age. 280 million years ago, the world was on the verge of the greatest mass extinction in Earth's history. The end-Permian event that would erase roughly 90% of all marine species and 70% of terrestrial vertebrate species. The forests Gulbrandsen found were growing just before that catastrophe. They represent ecosystems that were about to be swept away by a combination of volcanic activity, Atmospheric change and ocean chemistry disruption so severe that life on Earth came closer to total annihilation than at any other time in the fossil record. If Antarctic sediments preserve the transition across that boundary, the shift from living forest to devastated landscape, they could offer insights into the mechanisms of mass extinction that are difficult to obtain from better studied but more disturbed sites elsewhere. But the Permian forests are not the only chapter written into Antarctic rock. Fossil evidence spans a wide arc of geological time. During the Cretaceous period, roughly 100 million years ago, Antarctica supported forests of conifers and ferns alongside early flowering plants. Dinosaurs walked beneath those canopies, adapted to polar conditions in ways that are still being studied. By the Eocene epoch, around 50 million years ago, the continent still hosted forests. Though their composition had changed, flowering plants had diversified, the climate was warmer globally, and Antarctica, though positioned near the pole, experienced temperatures mild enough for subtropical vegetation along its coasts. Fossil pollen from Eocene sediments recovered by ocean drilling projects reveals a richness of plant life that seems almost impossible when measured against the continent's present state. The transition from that richness to the barren ice sheet of today did not happen in a single step. It was a long, uneven decline. Forests retreated from the interior first, pushed back by cooling temperatures and expanding ice. Coastal regions held on longer, sustained by oceanic warmth and maritime moisture. But as the circumpolar currents strengthened and thermal isolation deepened, even the coasts became inhospitable. The last forests may have clung to sheltered valleys along the Antarctic peninsula, persisting in pockets for millions of years after the interior had been claimed by ice. When they finally vanished, there was nothing left to replace them. The ice advanced over their remains and sealed them in place. What haunts the edges of this story is not the loss itself, but the incompleteness of the record. The fossils that have been found come from a tiny fraction of Antarctica's total area, the few percent where rock is exposed. The rest, the vast interior, the buried mountain ranges, the deep valleys now filled with ice, remains unsampled. If the margins of the continent have already yielded forests spanning hundreds of millions of years, what might the interior hold? Older forests, different species, records of transitions that are not preserved in any exposed outcrop. The fossils found so far are like words overheard through a closed door, enough to know that a conversation is happening inside, but not enough to follow the full thread. And the door, made of ice 4 kilometers thick, does not open easily. Behind it, pressed into stone and sediment, the rest of the story waits in the kind of darkness that only deep time and deep cold can provide. If the rocks beneath Antarctica hold the bones of its ancient past, the ice above them holds something equally extraordinary, but far more delicate. Not fossils, not minerals, air. Tiny pockets of atmosphere trapped inside frozen water, sealed at the moment snow compacted into ice and carried downward by the slow accumulation of everything that fell after them. These bubbles are not metaphors. They are not approximations or reconstructions inferred from chemical proxies. They are actual samples of Earth's atmosphere, preserved with a fidelity that no other natural archive can match, and they have transformed how humanity understands its own planet. The science of ice cores began modestly. Early drilling efforts in the mid-20th century were exploratory, testing whether useful information could be extracted from deep ice at all. The answer came quickly and emphatically. Each metre of ice core recovered from Antarctica's interior revealed layers that corresponded to specific periods in the past. Near the surface, individual years could sometimes be distinguished, marked by seasonal variations in crystal structure, dust content, and chemical composition. Deeper down, the layers thinned under pressure, compressing time into narrower and narrower bands, but the sequence remained intact. Older ice beneath younger ice, the order undisturbed, vertical timeline extending downward into the planet's memory. The Vostok ice core, drilled at a Soviet research station in the heart of East Antarctica, was among the first to reveal the full power of this archive. Completed in the late 1990s after decades of effort, it reached a depth of over 3,600 meters, penetrating ice that had formed more than 400,000 years ago. The gases trapped in that ice told a story that was already suspected, but had never been directly confirmed across such a span of time. Carbon dioxide and temperature rose and fell together, cycling through glacial and interglacial periods with a regularity that pointed to orbital forcing, the subtle changes in Earth's tilt, wobble, and orbital shape that alter how sunlight is distributed across the planet. During cold periods, carbon dioxide levels dropped. During warm periods, they rose. The correlation was tight, consistent, and unmistakable across 4 complete glacial cycles. But Vostok was only the beginning. The European project for ice coring in Antarctica, known as EPICA, pushed the record even further. Drilling at Dome C, one of the coldest and most remote locations on the continent, the project extracted ice dating back approximately 800,000 years. This extended the climate record through 8 glacial cycles, revealing patterns that had not been visible in the shorter Vostok record. One of the most striking findings was a shift in the rhythm of glacial cycles. Earlier in the record, cycles were shorter, roughly 40,000 years in duration. More recently, they lengthened to approximately 100,000 years. The reasons for this shift remain debated, but the fact that Antarctic ice captured it with such clarity allowed scientists to study the transition in detail, comparing atmospheric composition, temperature, dust levels, and volcanic signatures across the boundary. The ice does not limit itself to gases. It records temperature through the isotopic composition of the water molecules themselves. Not all water is chemically identical. Some molecules contain heavier isotopes of oxygen or hydrogen, and the ratio of these heavier isotopes to lighter ones changes depending on the temperature at which the snow originally formed. Warmer conditions favour a slightly different balance than colder ones. By measuring these isotope ratios layer by layer, scientists can reconstruct past temperatures with a precision that would seem impossible for events occurring hundreds of thousands of years ago, and yet the ice provides. It does not estimate. It records. Volcanic eruptions leave their own signatures. When a major eruption occurs, it sends sulfur compounds and fine ash high into the atmosphere, where winds carry them across the globe. Eventually, these particles settle out, falling onto ice sheets thousands of kilometers from the eruption itself. In Antarctic ice, volcanic layers appear as thin bands enriched in sulfate and sometimes containing microscopic shards of volcanic glass. These layers serve a dual purpose. They mark specific moments in time, allowing researchers to synchronize Antarctic records with volcanic chronologies established elsewhere. And they reveal the climatic impact of eruptions, showing how sulfur injections into the stratosphere can cause short-term cooling by reflecting sunlight before the particles eventually dissipate. Dust tells yet another story. During colder, drier periods in Earth's history, wind carried more mineral dust from exposed continental surfaces. Patagonia, southern Africa, and Australia all contributed dust that travelled thousands of kilometres before settling onto Antarctic ice. The amount and composition of this dust changed with climate. During glacial periods, when sea levels dropped and vegetation retreated, more land was exposed to wind erosion, and dust concentrations in the ice increased. During warmer interglacials, vegetation stabilized soils and dust levels fell. These variations provide a window into conditions on distant continents, recorded by ice that never left the pole. What emerges from all these layers is not a single narrative, but a symphony of overlapping signals. Temperature, atmospheric composition, volcanic activity, wind patterns, biological productivity, and orbital mechanics all leave traces in the same ice, interacting with each other across time in ways that reward patient analysis. The ice does not simplify, it preserves complexity, and it does so with a continuity that is rare in the natural world. Many climate records elsewhere are interrupted by erosion, tectonic disturbance, or biological activity. Antarctica's interior ice sheets, cold enough and stable enough to accumulate without significant melting for hundreds of thousands of years, provide an unbroken archive that allows scientists to see trends rather than fragments. Now the ambition reaches even deeper. A project known as Beyond Epica aims to recover ice that is approximately 1.5 million years old, pushing the continuous atmospheric record far beyond its current limit. If successful, it will capture the period when glacial cycles shifted from their earlier 40,000-year rhythm to the longer 100,000-year pattern that has dominated recent Earth history. Understanding why that transition occurred is one of the most important open questions in climate science, and the answer may be locked in ice that formed during the shift itself. But beneath the deepest ice lies something the cores cannot reach: sediments, rock, the interface between frozen atmosphere and buried continent. These layers predate the ice entirely, recording conditions from a time when Antarctica was still transitioning from a green world to a frozen one. If the ice cores are a library of atmospheric history, the sediments beneath them are the foundation on which that library was built. And the foundation in many places remains entirely unread. The ice has given extraordinary answers to questions about climate, atmosphere, and time. What it has not yet given is the full story of what existed before the ice itself arrived. That story lies deeper, in layers of stone and compressed earth that no drill has yet reached across most of the continent, waiting in the same patient darkness that has held everything else Antarctica has chosen not to reveal. From above, Antarctica presents the illusion of simplicity, a white surface, unbroken and featureless, stretching in every direction until it meets the sea or the sky. There are no visible ridges, no exposed cliffs, no valleys cutting through the landscape to hint at what lies beneath. The ice smooths everything, filling depressions, burying peaks, creating a topography so uniform that it seems almost artificial in its blankness. But that blankness is a lie. Beneath the ice, Antarctica is as rugged, as varied, and in some places as extreme as any terrain on the planet. The continent has mountains that no human eye has ever seen. It has valleys that no river has flowed through for millions of years. It has a geography that exists entirely in the dark, known only through the faint echoes of signals sent downward and the patterns they make when they bounce back. The discovery of this hidden landscape did not come from exploration in any traditional sense. No one climbed these mountains or walked these valleys. They were found by machines, by instruments that could see through ice the way sonar sees through water. Radar systems mounted on aircraft transmit signals that pass through ice but reflect off the rock beneath. By measuring the time it takes for the signal to return and the shape of the reflection, scientists can calculate depth, contour, and surface texture of the bedrock below. Over decades of airborne surveys, these measurements have been assembled into maps of a continent that exists in a dimension removed from ordinary perception, a world of stone concealed beneath a world of ice. What those maps revealed was not a simple basement of flat rock worn smooth by glacial grinding. It was a landscape of startling complexity. In East Antarctica, buried beneath the thickest part of the ice sheet, lies a mountain range that rivals the European Alps in both length and elevation. The Gamburtsev Mountains, first detected by a Soviet expedition in 1958 using seismic surveys, stretch for over 1,200 kilometers and rise to peaks exceeding 3,000 meters above their base. For decades after their initial detection, the Gamburtsevs remained poorly understood, their detailed structure obscured by the limitations of early measurement techniques. It was not until the AGAP project, the Antarctica's Gamburtsev Province Survey, conducted between 2008 and 2009, that their full character began to emerge. The AGAP survey combined airborne radar, gravity measurements, and magnetic data to produce the most detailed picture yet of a mountain range that no one has ever photographed from ground level. What it showed was unexpected. The Gamburtsefs are not smooth, eroded remnants of ancient peaks. They retain sharp ridges and deep valleys, features that on any exposed mountain range would indicate relative youth, or at least protection from the erosive forces that normally grind mountains down over geological time. But the Gamburtsefs are old, possibly dating back to the assembly of Gondwana itself, hundreds of millions of years ago. By rights, they should have been worn flat long ago. The explanation lies in the ice. In some regions of Antarctica, the ice sheet is what glaciologists call cold-based. This means the ice at the bottom is frozen to the bedrock beneath it, rather than sliding over a film of meltwater. Cold-based ice moves very slowly if at all, and because it does not slide, it does not erode. It sits on the rock like a protective shell, shielding the surface beneath from the grinding, scraping and plucking that warm-based glaciers inflict on their beds. The Gamburtsev Mountains appear to have been protected by cold-based ice for much of their buried history, preserved in something close to their pre-glacial form, while the rest of the world's mountain ranges were being steadily worn away by rain, rivers and moving glaciers. This preservation has implications beyond geology. If the mountains themselves have been protected, then the valleys between them may also retain ancient features. And indeed, radar surveys have revealed networks of valleys in the Gamburtsev region that bear the unmistakable signatures of river erosion rather than glacial carving. These valleys meander, they branch, they follow patterns consistent with flowing water responding to gravity over long periods of time. Glaciers do not carve this way. Glaciers tend to straighten valleys, deepen them into U-shapes, and leave behind characteristic deposits of ground-up rock. The valleys beneath the Gamburtsevs show none of these glacial traits. They appear to be relics of a hydrological system that operated when Antarctica was warmer and wetter, preserved beneath ice that arrived before later glacial activity could reshape them. Elsewhere beneath the continent, the terrain is even more extreme. The Bentley Subglacial Trench, located in West Antarctica, plunges to more than 2,500 meters below sea level, making it the lowest point on any continent not covered by ocean. If the ice were removed, this trench would be submerged, forming a deep marine channel. Its depth exceeds that of the Grand Canyon and approaches the scale of features normally associated with ocean floors rather than continental interiors. The existence of such a feature beneath the ice sheet complicates simple models of how the ice behaves. Ice resting in deep basins below sea level is in contact with the interface between land and ocean in ways that make it vulnerable to warming from beneath, particularly if warmer ocean water finds pathways into the subglacial environment. The topography beneath West Antarctica is generally more fragmented and lower than that beneath East Antarctica. Much of West Antarctica's bedrock lies below sea level, broken into basins and ridges by tectonic stretching and volcanic activity. This region includes active volcanic systems, most notably Mount Erebus, which remains one of the few continuously active volcanoes on the continent. Heat from volcanic and geothermal sources interacts with the base of the ice sheet, contributing to melting and influencing how ice flows. The combination of low-lying bedrock, volcanic heat, and ocean access makes West Antarctica's ice sheet inherently less stable than its eastern counterpart, a distinction that matters enormously for predictions of future ice loss and sea level change. What connects all of these buried features is the fundamental disconnect between surface and substance. Antarctica's visible face reveals nothing of the drama beneath it. The smooth white exterior conceals a continent of mountains and trenches, of ancient river systems and active volcanoes, of landscapes shaped by processes that predate the ice by hundreds of millions of years. This disconnect challenges the way humans tend to assign meaning based on appearance. The visible seems real, the hidden seems abstract. Antarctica inverts that relationship entirely. Its most significant features, the ones that determine how ice flows, how stable the ice sheet is, and how the continent will respond to future change, are all invisible. They exist only in data, in the reflected signals of radar and the subtle variations in gravitational pull that betray the presence of mass where the eye sees nothing. And among those invisible features, in the deep valleys and sealed basins where radar signals fade into ambiguity, there may be records older and more complete than anything yet recovered, waiting in a silence so total that even the instruments can only whisper at its edges. Beneath the ice that defines Antarctica, beneath the buried mountains and the ancient river valleys, there exists something that seems to contradict everything the continent represents. Water. Not frozen, not trapped in crystalline structure, but liquid, moving slowly through channels and pooling in basins that have not been touched by sunlight or open air for spans of time that stretch beyond comprehension. The idea of liquid water beneath one of the coldest surfaces on Earth sounds like a paradox. But Antarctica has never been a place that respects simple assumptions. It has always rewarded those who look past the obvious, and what lies beneath its ice sheet may be among the most extraordinary environments on the planet. The existence of subglacial lakes was not discovered by accident, nor was it predicted by theory alone. It emerged from observation, from patterns in radar data that did not fit expectations. When airborne radar surveys sent signals through the ice, most reflections returned rough and uneven, consistent with rock surfaces beneath the sheet. But, in certain locations, the reflections were startlingly smooth and bright, the kind of signal that liquid water produces. The boundary between ice and water creates a flat, mirror-like interface that reflects radar cleanly, unlike the irregular surface of stone. When these anomalous reflections began appearing in survey after survey, the implication became difficult to ignore. There was water down there, not in small amounts, not in transient melt pools that appeared and vanished. Substantial bodies of liquid water, persisting beneath kilometers of ice, maintained by conditions that exist nowhere else on Earth's surface. The physics that makes this possible is not exotic, but it requires a shift in perspective. Ice is an effective insulator. The deeper one goes beneath an ice sheet, the less influence surface temperatures have. At the same time, Earth's interior generates heat. Geothermal energy rises through the crust at a rate that is modest but continuous, warming the base of the ice sheet from below. Pressure also plays a role. The immense weight of kilometers of ice lowers the melting point of water at the base, a well-known physical principle that allows ice to melt at temperatures slightly below 0 degrees Celsius when subjected to sufficient pressure. Where these factors converge, geothermal warmth from below, insulation from above, and pressure throughout, ice at the base of the sheet melts, water forms, and because it has nowhere to go, it accumulates. Today, scientists have identified more than 400 subglacial lakes beneath the Antarctic ice sheet. They range enormously in size. Some are little more than ponds, detectable only as subtle anomalies in radar data. Others are vast. The most famous, and the most studied, is Lake Vostok, located beneath Russia's Vostok research station in East Antarctica. Lake Vostok is enormous by any measure. Its surface area is comparable to that of Lake Ontario. It stretches roughly 250 kilometers in length and reaches depths of over 500 meters in places. Above it sits nearly 4 kilometers of ice, pressing down with a weight that has kept the lake sealed from the atmosphere for an estimated 15 to 34 million years. The water inside has never evaporated, never been rained into, never been stirred by wind. It exists in a state of isolation so profound that it challenges the imagination to conceive of what such an environment might contain. The Russian drilling program at Vostok became one of the most ambitious and contentious projects in Antarctic science. Beginning in the 1970s and continuing over decades, the drill descended slowly through the ice sheet, passing through layers of compressed snow that recorded hundreds of thousands of years of atmospheric history. As it approached the lake's surface, concerns mounted. The drilling fluid used to keep the borehole open, a mixture of kerosene and freon, posed a contamination risk. If surface microbes or industrial chemicals entered the lake, they could irreversibly alter an environment that had been pristine for geological eons. In February 2012, the drill finally breached the ice water interface. Lake water rushed upward into the borehole and froze, creating a plug of refrozen lake water that could be sampled without directly entering the lake itself. The samples were analysed for signs of life, and preliminary results suggested the presence of microbial DNA, though debate over contamination complicated interpretation. A different approach was taken at Lake Whillans, a smaller subglacial lake beneath the West Antarctic ice sheet. In January 2013, a team using a specially designed hot water drill penetrated the ice and reached the lake using equipment that had been meticulously sterilized. The water and sediment samples they retrieved provided the first unambiguous confirmation of microbial life in a subglacial Antarctic lake. The organisms found were not complex. They were bacteria and archaea, single-celled life forms adapted to conditions of extreme cold, total darkness, and limited nutrients. But their very existence was significant. These microbes did not rely on sunlight for energy. They sustained themselves through chemolithotrophic metabolism, deriving energy from chemical reactions between minerals and water. Life, it turned out, did not require the sun. It required only chemistry and time. The implications of this discovery extend well beyond Antarctica. If microbial life can persist in sealed, sunless, nutrient-poor environments beneath kilometers of ice for millions of years, then the boundaries of habitability are wider than previously assumed. This has direct relevance to the search for life beyond Earth. Jupiter's moon, Europa, and Saturn's moon Enceladus both possess subsurface oceans beneath icy crusts, environments that bear a striking resemblance to Antarctica's subglacial lakes. The conditions that sustain microbial life beneath the Antarctic ice sheet, geothermal heat, mineral-water interactions, isolation from surface processes, are not unique to Earth. They are planetary processes that could occur wherever ice and rock and heat coexist. But the lakes hold more than biological questions. They're also geological messengers. Water trapped beneath ice dissolves minerals from the bedrock it contacts, carrying chemical signatures that reveal the composition of rock in regions where direct sampling is impossible. Some subglacial lakes sit atop ancient sediment layers deposited when Antarctica was ice-free. Those sediments may contain organic material, microfossils, and chemical records of ancient climates that predate the ice by tens of millions of years. If sampled carefully, they could extend the climate record far beyond the reach of ice cores, bridging the gap between the frozen archive above and the geological record below. The subglacial water system is not static. Lakes fill and drain over time, releasing water into downstream channels and refilling from upstream melt. Satellite measurements have detected subtle changes in ice surface elevation associated with these drainage events, ice rising slightly as water accumulates beneath and sinking as it flows away. These movements reveal a dynamic, interconnected hydrological network operating entirely out of sight, linking lakes separated by hundreds of kilometers. This hidden circulation lubricates the base of the ice sheet, influencing how fast glaciers move and how stable the ice above remains. In the sealed darkness beneath the continent, water that has not seen the sky for millions of years continues to shape the world above it, quietly, persistently, and with consequences that scientists are only beginning to trace. There is a particular kind of intimacy in reading the air that someone else breathed. Not someone exactly, but something, a world, a moment, an entire planetary state captured in a pocket of gas no larger than a grain of rice. When scientists crack open a segment of Antarctic ice and release the bubbles sealed inside, they are not performing an abstract measurement. They're opening a window that has been shut for tens of thousands of years, sometimes hundreds of thousands, and letting the atmosphere of a vanished Earth escape into a laboratory where instruments wait to catch it. The air does not speak in words. It speaks in ratios, in parts per million, in isotopic signatures so faint that detecting them requires machines of extraordinary sensitivity. But what it says, when translated, is among the most important testimony the planet has ever offered about itself. The process begins with snowfall. When snow lands on the Antarctic interior, it does not melt. It sits, accumulates, and is gradually buried by the snow that follows. As layers build, the weight of the overlying snow compresses the lower layers, squeezing out the spaces between crystals. Air that was initially free to move through the porous snow becomes progressively trapped. At a depth of roughly 60 to 100 meters, depending on local conditions, the snow is compacted into a transitional form called firn, a dense granular material that is no longer loose snow, but not yet solid ice. Below that boundary, compression seals the remaining air pockets entirely. They become bubbles, imprisoned in ice, cut off from the atmosphere above. Whatever gases were present at the moment of sealing remain inside, unchanged, until someone or something opens the ice again. This is why Antarctic ice cores are considered among the most direct records of past atmospheric composition available to science. They do not infer what the atmosphere contained. They contain it. Carbon dioxide, methane, nitrous oxide, and traces of other gases can be measured directly from the trapped air. When researchers at the Vostok station analysed gases from their deep ice core in the late 1990s, the results drew a picture that was both elegant and sobering. Over 400,000 years, carbon dioxide concentrations had oscillated between roughly 180 parts per million during glacial periods and 280 parts per million during warm interglacials. Temperature, reconstructed from isotope ratios in the surrounding ice, followed the same rhythm. The two curves rose and fell together, cycle after cycle, locked in a relationship that left little room for doubt about their connection. The Epica Dome Sea core extended this record to 800,000 years, confirming the pattern across additional glacial cycles and revealing the shift in cycle duration that occurred midway through the record. But it also showed something that the shorter record had only hinted at. The relationship between carbon dioxide and temperature was not simply one of cause and effect operating in a single direction. In some transitions, warming appeared to begin slightly before carbon dioxide levels rose, suggesting that initial temperature increases, perhaps triggered by orbital changes, caused the oceans to release stored carbon dioxide, which then amplified the warming through this greenhouse effect. In other transitions, the sequence was less clear. The interplay between temperature and atmospheric composition emerged as a feedback system, not a simple chain of cause and consequence, but a loop in which each variable influenced the other. Methane told its own story. Unlike carbon dioxide, which is primarily exchanged between the atmosphere and the oceans, methane is closely linked to biological activity on land, particularly in wetlands. When ice core records showed methane levels rising during warm periods, it indicated that wetlands were expanding in the tropics and northern latitudes, releasing more of the gas as vegetation decomposed in waterlogged soils. During cold periods, methane dropped as wetlands shrank and biological activity slowed. These variations provided a window into conditions on continents far from Antarctica, recorded in ice that never left the pole. The frozen South was listening to the rest of the world and writing down what it heard. Dust layers added another dimension. During glacial periods, when the planet was colder and drier, winds picked up more mineral dust from exposed continental surfaces. This dust travelled thousands of kilometres before settling onto the Antarctic ice sheet, where it accumulated in concentrations that varied with climate. Analysis of the dust's mineral composition could identify its origin, often tracing it to Patagonia, southern Australia, or the dry plains of southern Africa. The amount of dust in each layer reflected conditions in those distant regions, how arid they were, how much vegetation covered the soil, how strong the winds blew. Antarctica's ice was not just a local record, it was a global sensor, capturing signals from across the planet and preserving them in sequence. Volcanic eruptions punctuated the record with sharp chemical spikes. Sulfate concentrations jumped in layers corresponding to major eruptions, marking moments when volcanic gases reached the stratosphere and spread across the globe. Some of these spikes could be matched to known eruptions documented in geological records elsewhere, providing precise time markers that allowed Antarctic ice chronologies to be synchronized with records from Greenland, tropical ice caps, and marine sediments. This synchronization revealed that some climate events were global, occurring simultaneously in both hemispheres, while others were asynchronous, appearing first in one hemisphere before propagating to the other. The bipolar seesaw, as this pattern came to be known, pointed to the role of ocean circulation in transferring climate signals between north and south, with the Southern Ocean acting as a critical intermediary. Against all of these natural variations spanning hundreds of thousands of years of glacial and interglacial cycling, one feature of the modern record stands in stark contrast. In the uppermost layers of Antarctic ice, carbon dioxide concentrations rise sharply, departing from the range that characterized every previous cycle in the record. The increase is not gradual. It does not follow the slow orbital rhythms that governed earlier transitions. It appears as a steep upward line, crossing thresholds that were never exceeded in 800,000 years of recorded oscillation. The ice does not comment on this departure. It does not assign cause or predict consequence. It merely records the numbers, preserving them alongside the dust and ash and ancient air with the same indifference it has shown to everything else. But the contrast is visible to anyone who looks at the data. Against the long, rhythmic breathing of the planet recorded in deep ice, the modern signal does not look like breathing at all. It looks like something else entirely, and the ice leaves it to the reader to decide what that something might be. Extinction, when it is remembered at all, tends to be remembered loudly. The mind reaches for fire, for impact, for the sudden darkness of a world thrown off its axis in a single terrible moment. These images persist because they are dramatic, because they compress unimaginable loss into a frame small enough for human comprehension. But most extinction does not work that way. Most extinction is quiet. It moves through ecosystems the way a tide retreats from a shoreline, so slowly that no single wave seems significant until the water has gone entirely and the sand lies bare. Antarctica knows this kind of extinction intimately. It did not lose its living world in a flash. It lost it grain by grain, species by species, layer by layer over millions of years, and the record of that loss is among the most complete and undisturbed on Earth. The evidence is written in pollen, microscopic grains, nearly indestructible, shed by plants that once grew across a continent now buried under ice. Pollen grains are remarkable archives. Their outer walls, composed of a substance called sporopollenin, resist decay with a stubbornness that borders on geological permanence. They survive in sediments long after the plants that produced them have vanished. And because different plant species produce pollen grains of distinctive shapes and surface patterns, identifying them under a microscope allows researchers to reconstruct ancient vegetation with surprising specificity. What the pollen record from Antarctic sediments reveals is not a sudden disappearance but a prolonged simplification, a narrowing of diversity that unfolded across millions of years as the continent cooled and its ecosystems contracted. In older sediment layers, pollen assemblages are rich and varied. Multiple families of trees, shrubs, ferns, and flowering plants appear together, indicating ecosystems of considerable complexity. Nothofagus is present, alongside conifers, proteaceous shrubs, and a range of understory species. These communities resemble the temperate rainforest that still exists today in southern Chile, Tasmania, and New Zealand, ecosystems characterized by high moisture, moderate temperatures, and dense canopy cover. The diversity suggests stability, an environment capable of supporting many species simultaneously over long periods without dramatic disruption. As the layers ascend, the picture changes. Certain pollen types become rarer, some disappear entirely. The assemblage narrows, dominated by fewer species, typically those best adapted to cooler temperatures and shorter growing seasons. Nothofagus persists longer than most, its tolerance for cold and its deep evolutionary roots in southern high latitudes giving it an advantage that other genera could not match. But even Nothofagus eventually fades from the record, its pollen grains becoming sparse and then absent as condition crossed thresholds that no temperate tree could survive. What replaces it is not another forest, it is emptiness. The pollen record does not shift to a different kind of vegetation, it simply stops. This pattern of decline was not uniform across the continent. Coastal regions, moderated by oceanic influence, retained vegetation longer than the interior. The Antarctic Peninsula, which extends northward towards South America, appears to have been a final refuge, a narrow strip of land where maritime conditions sustained plant life long after the main body of the continent had been claimed by ice. Fossil evidence from the peninsula suggests that pockets of shrubby vegetation and perhaps even small trees persisted into the late Neogene, millions of years after the interior had frozen. These holdouts were not thriving ecosystems, they were remnants, the last expression of a biological heritage that once spanned the continent, compressed into shrinking enclaves by ice that advanced from every direction. The animals that once inhabited these ecosystems are harder to trace. Fossil preservation of vertebrates and insects requires specific conditions that are less common in Antarctic settings than the preservation of pollen and wood. But the available evidence, supplemented by inference from related species found on other southern continents, suggests that Antarctica's cooling drove waves of migration northward. Species capable of crossing narrowing land bridges or dispersing across newly forming ocean gaps carried their lineages away from the pole. Those that could not migrate faced the same narrowing of habitat that the plants experienced, a slow compression of livable space until nothing remained. The biogeographic consequences of this dispersal are still visible today. Southern beech forests in Patagonia, in Tasmania, and New Zealand share ancestry that traces back to a time when Antarctica connected these regions. The distribution of certain insect families, freshwater fish, and marsupials across the southern continents follows patterns that make sense only if Antarctica once served as biological corridor, a central hub through which lineages passed before the ice cut them off. When that hub froze, it did not just lose its own species, it severed connections that had shaped evolution across an entire hemisphere. The isolation that followed forced each fragment of the former Gondwanan biota to evolve independently, diverging along separate paths that would never reconverge. What makes Antarctica's extinction record particularly valuable is its clarity. On other continents, extinction is followed by recovery. New species arrive, ecosystems reorganize. The evidence of loss is obscured by the evidence of renewal. In Antarctica, recovery did not occur. Once ice sheets became established and temperatures fell below the thresholds required for terrestrial plant life, the continent entered a state from which it has not returned. There was no recolonization, no succession of new communities, no overwriting of the old record by new biological activity. The ice preserved the endpoint. The last pollen grain sits in its layer undisturbed, marking the moment when a continent's biological voice fell silent. This finality offers a kind of precision that is rare in the study of extinction. There is no ambiguity about whether a species disappeared temporarily or permanently. There is no confusion caused by later arrivals that might resemble earlier inhabitants. The record is clean, not because the loss was simple, but because nothing came afterward to complicate it. And within that clean record lies information about how ecosystems respond to sustained environmental pressure, how diversity narrows before collapse, how certain species hold on longer than others, and why. These patterns are not confined to the past. They describe processes that operate wherever environmental conditions shift faster than biological adaptation can follow. The difference is that Antarctica recorded them with unusual fidelity, sealed them under ice, and held them in place for science to eventually find. The continent's silence is not emptiness. It is the sound of an ecosystem that spoke for millions of years, grew quieter and quieter, and then stopped, leaving behind only the faintest trace of everything it once had to say. The story of life on Earth is often told as a series of dramatic transitions, each one sweeping away what came before and replacing it with something new. Dinosaurs ruled, then vanished. Mammals rose, then diversified. Humans arrived, then reshaped everything. These transitions feel clean in the retelling, as if the planet turned the page and started fresh each time. But the reality is far messier, far slower, and far more dependent on circumstance than any summary can capture. Between the age of dinosaurs and the age of humans lies a vast stretch of time that is neither as well documented nor as well understood as the periods on either side of it. And Antarctica, which was present and active throughout that entire stretch, may hold some of the most important records of what actually happened during those missing millions of years. Dinosaurs did not avoid Antarctica. The continent was not too cold, not too remote, not too inhospitable for them during the Mesozoic era. It was part of Gondwana, positioned at high southern latitudes, but warmed by global climates that were far milder than today's. Forests covered the land, rivers carved the surface, and among the creatures that inhabited those forests were dinosaurs adapted to conditions that would seem extreme by modern standards. Including months of continuous darkness during polar winter, their fossils have been found, not in abundance, but in enough quantity and diversity to confirm that Antarctica was part of the dinosaur world rather than excluded from it. Cryolophosaurus, a large predatory dinosaur discovered in the Transantarctic Mountains in 1991, dates to the early Jurassic period, roughly 190 million years ago. Its name means frozen crested lizard, a reference to the distinctive bony crest on its skull and to the icy conditions under which it was found, though the world it actually inhabited was nothing like the frozen landscape that entombed it. Cryolophosaurus lived in a forested environment, hunting prey in an ecosystem that bore no resemblance to modern Antarctica. Its discovery confirmed that large theropod dinosaurs ranged into polar latitudes, challenging earlier assumptions that such animals were confined to warmer regions. Later in the Mesozoic, during the Cretaceous period, Antarctica continued to host dinosaurs. Antarctopelta, an armoured dinosaur found on James Ross Island near the Antarctic Peninsula, dates to roughly 70 million years ago, close to the end of the Cretaceous, not far in geological time from the mass extinction event that would eliminate all non-avian dinosaurs worldwide. Its presence suggests that Antarctica's ecosystems were still functioning, still supporting complex food webs, right up until the catastrophe struck. When the asteroid impact or volcanic upheaval or combination of factors brought the Cretaceous to its violent close roughly 66 million years ago, Antarctica did not escape the consequences. Its dinosaurs vanished along with their counterparts on every other continent. But what happened next is where Antarctica's story diverges from the familiar narrative. On most continents, the aftermath of the end Cretaceous extinction was a period of rapid evolutionary innovation. Mammals, which had existed as small ecologically marginal creatures throughout the age of dinosaurs, suddenly found themselves in a world emptied of dominant competitors. They diversified explosively, filling ecological niches that had been occupied by dinosaurs for over 100 million years. Birds, the surviving lineage of dinosaurs, also radiated into new forms. Flowering plants spread and reshaped terrestrial ecosystems. The world reorganized, and it did so relatively quickly by geological standards. In Antarctica, that reorganization was constrained. The continent was already cooling. Its connections to neighboring land masses were weakening as Gondwana continued to fragment. The pathways that would have allowed new species to colonize, or existing species to migrate and diversify, were narrowing. Mammals did appear in Antarctic fossil records from the Eocene epoch, roughly 40 to 50 million years ago, but their presence was limited and apparently short-lived. The remains of marsupial-like mammals found on Seymour Island suggest that some lineages crossed from South America when a land connection or near connection still existed. But as temperatures dropped and habitats shrank, these early Antarctic mammals could not establish the kind of diverse, self-sustaining populations that their relatives were building on warmer continents. This is a crucial point, one that Antarctica's record makes with a clarity not easily found elsewhere. The rise of mammals after the dinosaurs was not an inevitable process powered by some internal drive toward complexity. It was contingent on environmental conditions. Where those conditions were favourable, where climates were warm, habitats were extensive, and ecological niches were available, mammals diversified rapidly. Where conditions were hostile, where cooling was already underway and isolation was increasing, diversification stalled. Antarctica shows what happens when the usual post-extinction recovery is suppressed by environmental reality. It became a filter rather than a cradle, allowing only brief passage before closing its doors entirely. The plant record tells a parallel story. Flowering plants, which had been diversifying globally throughout the late Cretaceous and into the early Cenozoic, did not flourish in Antarctica after the extinction event. Pollen records from this interval show communities under stress rather than expansion. Diversity declined instead of increasing, a pattern that contrasts sharply with what was happening at lower latitudes. The continent that had once supported rich forests was being pushed toward biological simplicity at precisely the moment when the rest of the world was experiencing one of the greatest expansions of terrestrial life in Earth's history. This asymmetry is important because it reveals how unevenly the planet recovers from catastrophe. The end Cretaceous extinction was a global event, but the recovery was profoundly local. Geography, climate, and connectivity determined which regions became centres of innovation and which became dead ends. Antarctica, caught between a global biological reset and a local climate deterioration, became a place where the old world ended but the new one never fully arrived. Its fossils from this transitional period capture a landscape in decline, an ecosystem simplifying under pressure, a continent that was running out of time even as the rest of the world was beginning again. What makes these records especially valuable is that they were sealed before they could be overwritten. On other continents, the post-extinction recovery eventually obscured the immediate aftermath. New ecosystems developed. New species replaced old ones. The evidence of the difficult transitional period was buried under later biological activity. In Antarctica, the ice came before the overwriting could occur. The transitional record, incomplete as it may be, was frozen in place, preserved beneath conditions that prevented further disturbance. If those records can be accessed, if drilling and sampling can reach the right layers in the right locations, they could fill gaps in the story of how Earth moved from one dominant biological regime to another, revealing not just what survived the extinction, but what happened in the uncertain, constrained, and largely unexamined space between what was lost and what eventually replaced it. There is a map that has troubled historians and cartographers for over 500 years. It was drawn in 1513 by Piri Reis, an Ottoman admiral and navigator, on a piece of gazelle skin. The map depicts the western coast of Africa, the eastern coast of South America, and along the bottom edge, a landmass that some have argued bears a resemblance to the northern coastline of Antarctica. This last detail is what gives the map its enduring power to provoke. In 1513, Antarctica had not been officially sighted. European explorers would not lay eyes on it for another 3 centuries. The continent would not be mapped with any accuracy until the 19th and 20th centuries. And yet there it is, or something like it, drawn on parchment by a man who claimed his sources included older maps, some dating back to the time of Alexander the Great. The Piri Reis map is not the only old chart to suggest knowledge of a southern landmass. The Orontius Phineus map of 1531 shows a large continent centred on the South Pole with features that some researchers have compared to the subglacial topography of Antarctica, the shape of the land beneath the ice, rather than the ice-covered coastline visible today. The Haji Ahmed map of 1559, the Philippe Boitier map of 1737, and others from the age of exploration all depict southern land masses of varying shapes and sizes, some with interior details that seem oddly specific for regions that were supposedly unknown. Mainstream scholarship has generally explained these maps as products of cartographic convention rather than actual observation. For centuries, European mapmakers operated under the influence of an ancient geographical idea, the concept of terra australis incognita, the unknown southern land. This hypothetical continent was rooted not in exploration but in philosophy. Ancient Greek thinkers, particularly Aristotle and later Ptolemy, proposed that the land masses of the northern hemisphere must be balanced by an equivalent mass in the south, a principle of cosmic symmetry that felt intuitively correct even without evidence. This idea persisted through the Roman period, survived the Middle Ages, and was carried forward into the Renaissance, where mapmakers routinely included a large southern continent on their charts as a placeholder, a space reserved for land that logic suggested must exist even if no one had confirmed it. This explanation accounts for most of the maps. Terra Australis appeared in various forms on charts throughout the 16th, 17th and 18th centuries, its size and shape shifting with each iteration as explorers pushed further south without finding the expected continent. Each expedition that failed to discover land in the Southern Ocean trimmed the hypothetical continent a little more, until eventually the placeholder was reduced to the actual Antarctic coastline first glimpsed in the early 1800s. From this perspective, the maps do not reflect hidden knowledge. They reflect educated guessing refined over centuries by the slow accumulation of negative evidence. But not everyone has found this explanation satisfying. In 1966, Charles Hapgood, a professor of history at Keene State College in New Hampshire, published a book titled Maps of the Ancient Sea Kings. Hapgood's argument was provocative. He proposed that certain medieval and Renaissance maps, including the Piri Reis map, were not based on contemporary knowledge or philosophical speculation, but were copies of far older source maps, originating from a civilization that had surveyed the Earth at a time when Antarctica was free of ice. Hapgood did not claim to know who this civilization was. He did not attribute the maps to any specific culture, but he argued that the accuracy of certain coastal features, particularly on the Piri Reis map, could not be explained by the cartographic knowledge available in the 16th century, and must therefore reflect a lost tradition of geographical expertise. Hapgood's hypothesis was controversial from the moment it appeared. Most professional cartographers and historians rejected it, pointing out that the resemblance between the Piri Reis map's southern landmass and Antarctica's actual coastline is approximate at best and requires selective interpretation. The map contains numerous errors and distortions that are inconsistent with a precise survey. The southern landmass depicted may represent the South American coastline itself, bent eastward due to the projection method Piri Reis used, rather than a separate continent. These critiques are substantial and widely accepted within academic circles, and yet the idea refuses to disappear entirely. Graham Hancock, a journalist and author whose work has focused on the possibility of lost civilizations, revived and expanded Hapgood's arguments in the 1990s. Hancock proposed that a technologically capable civilization existed during the last ice age, prior to roughly 12,000 years ago, and that this civilization possessed navigational and cartographic skills that were lost when catastrophic environmental changes destroyed it. Antarctica, in Hancock's framework, became a potential site for the remains of such a civilization, its evidence buried beneath ice that had accumulated since the end of the last glacial period. These claims sit well outside the boundaries of mainstream archaeology and geology, and they have been extensively criticized by specialists in those fields. The geological evidence strongly indicates that Antarctica's ice sheet formed tens of millions of years ago, not thousands, making the idea of a recent ice-free Antarctica untenable by conventional scientific understanding. But the persistence of these ideas reveals something that extends beyond the specific claims themselves. The maps, whether they depict real knowledge or inherited imagination, speak to a deep human intuition that the bottom of the world holds something significant, something that was known and then forgotten, seen and then obscured. This intuition does not require lost civilizations to be meaningful. It reflects a genuine tension between what is known and what is concealed, between the accessible surfaces of the planet and the vast hidden spaces that resist investigation. What is undeniable is that Antarctica was once ice-free. Forests grew there, rivers flowed, complex ecosystems flourished for hundreds of millions of years. These are not speculative claims. They're confirmed by fossil evidence, sediment records, and geological analysis. The question is not whether Antarctica had a different past, but whether any knowledge of that past, however distorted, could have survived in cultural memory across the kind of time spans involved. Science says no, and the evidence supports that conclusion firmly. But the maps linger in the imagination because they represent a deeper question that science has not fully answered. Not whether ancient people mapped Antarctica, but whether the planet still holds chapters of its own story that remain fundamentally out of reach, sealed beneath ice that has proven more patient, more persistent, and more secretive than any human institution has ever managed to be. Antarctica does not confirm what we already believe about the history of Earth's climate. It complicates it. Every ice core drilled, every sediment layer sampled, every radar survey flown across its interior has added not simplicity but dimension, not closure but depth. The continent has a way of answering one question while quietly opening three more behind it, and the cumulative effect is a picture of planetary behaviour that is far less orderly, far less predictable, and far more sensitive to disruption than earlier models suggested. If Antarctica has a single lesson to offer the study of climate, it is that the systems governing this planet do not operate in straight lines. They operate in thresholds, in feedbacks, in sudden reorganizations that can remain invisible until they're already underway. One of the most important contributions Antarctica has made to climate science is the discovery that the two hemispheres of the Earth do not always change in lockstep. For a long time, the assumption was that major climate shifts, particularly the transitions between glacial and interglacial periods, propagated uniformly across the globe. When ice advanced in the north, it advanced in the south. When temperatures rose in one hemisphere, they rose in the other. Antarctic ice cores challenged this assumption directly. Careful comparison between Antarctic records and ice cores from Greenland revealed a pattern that has come to be known as the bipolar seesaw. In many transitions, warming in one hemisphere corresponds to cooling in the other, as if the planet's heat budget were being redistributed rather than uniformly increased or decreased. The mechanism behind this seesaw involves ocean circulation, particularly the Atlantic meridional overturning circulation, a massive system of currents that transports warm water northward at the surface and returns cold water southward at depth. When this circulation weakens, as it appears to have done during certain rapid climate events in the past, heat accumulates in the Southern Ocean instead of being carried north. Antarctica warms while the North Atlantic cools. When the circulation strengthens again, the pattern reverses. These shifts are not subtle. They involve temperature changes of several degrees occurring over decades or centuries, fast enough to reshape ecosystems and alter atmospheric patterns across both hemispheres. Antarctic records capture these events with a precision that allows scientists to determine not only that they occurred, but how they unfolded in time. The sequence matters. Knowing whether Southern Hemisphere warming preceded or followed Northern Hemisphere change helps distinguish between different mechanisms and test competing hypotheses about what drives rapid climate shifts. Without Antarctica's ice core archive, this kind of analysis would be impossible. The Southern record provides the counterpoint necessary to understand the global system as a whole rather than as a collection of regional stories. Beyond the bipolar seesaw, Antarctica has forced a rethinking of how ice sheets themselves participate in climate change. For much of the history of climate science, ice was treated as a passive indicator, growing when it was cold and shrinking when it was warm, reflecting climate rather than driving it. Antarctic research has revealed a more complex role. Ice sheets are not merely responders, they're active agents in the climate system, capable of amplifying change through feedback mechanisms that operate on multiple timescales. The most obvious of these feedbacks is albedo. Ice reflects far more incoming solar radiation than open water or bare land. As ice sheets expand, they increase the planet's reflectivity, reducing the amount of energy absorbed from the sun and reinforcing cooling. As ice retreats, darker surfaces are exposed, absorbing more energy and reinforcing warming. This feedback is powerful and well understood, but it is not the only way ice influences climate. Ice sheets alter ocean circulation by producing meltwater that changes the salinity of surrounding seas. They depress the land beneath them, altering atmospheric circulation patterns. They store enormous volumes of fresh water that, when released, can reshape coastal geography and marine ecosystems across the globe. The Andrill project, which drilled into seafloor sediments beneath the Ross Ice Shelf in Antarctica, provided some of the clearest evidence yet of how dynamic Antarctic ice has been over geological time. The sediment cores recovered by Andrill revealed that the ice sheet had advanced and retreated dozens of times over the past few million years, oscillating between states of extensive coverage and significant reduction in response to changes in ocean temperature and atmospheric composition. These oscillations were not uniform. Some retreats were modest, others were substantial, suggesting that large portions of the West Antarctic ice sheet may have collapsed during warm periods that were not dramatically warmer than the present. This finding carries significant implications. If the ice sheet responded that sensitively to past warming events, even those that were relatively moderate by geological standards, then its stability under current and projected future warming becomes a question of immediate practical importance. The Andrill record does not predict what will happen, but it constrains the range of possibilities by showing what has happened before under comparable conditions. It demonstrates that the ice sheet is not a permanent feature in the way that human perception tends to assume. It is a conditional one, maintained by a balance of forces that can shift. Antarctica has also revealed the importance of non-linear response in climate systems. Linear models assume that small changes in forcing produce proportionally small changes in outcome. Double the perturbation, double the effect. But Antarctic records show that this assumption frequently fails. Ice sheets can remain stable for long periods under gradually changing conditions, absorbing small perturbations without visible response. and then undergo rapid reorganization once a critical threshold is crossed. These tipping points are not always predictable in advance. They emerge from the interaction of multiple factors: ice dynamics, ocean heat transport, bedrock topography, atmospheric composition, that individually may seem manageable but collectively can push the system past a point of no return. The concept of irreversibility is perhaps the most sobering insight Antarctica offers to climate science. Some past ice retreats appear to have reached states from which recovery was impossible under the same climate conditions. Once grounding lines retreated past certain topographic features, once warm water gained access to subglacial basins, the process of ice loss became self-sustaining even without additional forcing. The ice did not simply bounce back when conditions stabilized. It continued to retreat until a new equilibrium was established, often involving significantly less ice than before. These episodes are recorded in Antarctic sediments and in the geometry of the ice sheet itself, and they suggest that stability should not be confused with resilience. What Antarctica ultimately adds to the story of Earth's climate is not a single corrective, but a change in perspective. The climate system is not a machine with predictable outputs for given inputs. It is a web of interactions, sensitive to initial conditions, subject to thresholds, and capable of surprises that cannot always be anticipated from first principles alone. Antarctica's records, spanning hundreds of thousands of years of atmospheric history and millions of years of ice dynamics, provide the empirical evidence needed to take that complexity seriously. The continent does not simplify our understanding, it deepens it, adding layers of nuance that make the picture more accurate and, in its accuracy, more urgent. There is a frontier beneath Antarctica that science has only recently begun to approach with the tools necessary to comprehend it. Not the ice itself, which has been studied for decades, but the deeper layers, the older questions, the environment so remote and so difficult to reach that even defining what they contain requires technologies that did not exist a generation ago. The continent has always resisted easy understanding, but what is becoming clear, as instruments grow more sensitive and ambitions push further, is that the boundary of the unknown in Antarctica is not retreating, so much as revealing itself to be deeper, more layered, and more interconnected than anyone had anticipated. The Beyond Epica project represents one of the most ambitious attempts to push past current limits. Its goal is to recover ice that is approximately 1.5 million years old, nearly twice the age of the oldest continuous ice record currently available. The target site is a region of East Antarctica where ice accumulation rates are low and the ice sheet has remained stable for an extraordinarily long period. If the project succeeds, it will penetrate into a period of Earth climate history known as the Mid-Pleistocene Transition, a stretch of time between roughly 1.2 million and 700,000 years ago, when the rhythm of glacial cycles shifted from a pattern dominated by 40 000-year intervals to one dominated by 100 000-year intervals. This shift is one of the most important unresolved questions in paleoclimatology. The orbital forces that drive glacial cycles did not change during this period. Something within the Earth's internal climate system reorganized, altering how the planet responded to the same external forcing. Understanding what changed, and why, could reshape how scientists think about the sensitivity of ice sheets and the stability of the climate system as a whole. But ice, no matter how old, only tells part of the story. Beneath the deepest ice lies another archive entirely, one composed not of frozen air and compressed snow, but of sediment, rock, and the molecular remnants of biological and chemical processes that predate the ice by tens of millions of years. These subglacial sediments sit at the interface between ice and bedrock, in some cases resting undisturbed since before Antarctica froze. Accessing them is extraordinarily difficult. It requires drilling through the full thickness of the ice sheet, maintaining sterile conditions to prevent contamination, and recovering material that may be fragile, waterlogged, or compressed to the point of ambiguity. Yet the potential rewards are immense. These sediments could preserve microfossils, organic molecules, and chemical signatures from periods when Antarctica was transitioning from a vegetated, ice-free continent to the frozen desert it has become. They could bridge the gap between the ice core record and the geological record, linking atmospheric history to biological and tectonic history across a continuous timeline. Exploration beneath the ice shelves has also entered a new phase. Autonomous underwater vehicles designed to operate beneath floating ice in conditions where human presence is impossible have begun mapping the underside of Antarctica's ice shelves with unprecedented detail. These vehicles navigate through dark, near-freezing water, collecting data on ice thickness, ocean temperature, salinity, and the topography of the seafloor beneath. What they've found in several locations is warmer water intruding beneath ice shelves from the deep ocean, reaching grounding lines where ice transitions from floating to resting on bedrock. This warm water melts ice from below, thinning shelves and potentially destabilizing the glaciers they buttress. The process is invisible from the surface, detectable only through the subtle instruments carried by machines that venture where humans cannot follow. The coupling between ice, ocean, bedrock and atmosphere is emerging as one of the most critical and least understood aspects of Antarctic science. For decades, these components were studied largely in isolation. Ice dynamics were modelled separately from ocean circulation. Bedrock topography was treated as a static boundary condition rather than an interactive variable. Atmospheric forcing was applied uniformly rather than accounting for regional differences in wind patterns, moisture transport, and temperature gradients. What contemporary research is revealing is that these systems are not merely connected. They're coupled in ways that produce behaviours none of them would exhibit alone. Warm ocean water penetrating beneath an ice shelf does not simply melt ice. It changes the pressure distribution on the bedrock, alters subglacial water flow, modifies the stress patterns within the ice, and feeds back into ocean circulation by changing the volume and temperature of meltwater returned to the sea. The biological dimension of this interconnected system is also gaining attention. The discovery of microbial life in subglacial lakes and beneath ice shelves has opened questions that extend far beyond biology. If organisms have survived for millions of years in sealed environments beneath Antarctic ice, they have done so by exploiting chemical energy sources derived from mineral water interactions. Their metabolisms, shaped by conditions of extreme isolation, limited nutrients and no sunlight, may represent some of the oldest continuously functioning biological systems on the planet. Studying them is not merely a question of cataloguing extremophiles, it is a question of understanding the limits of life itself, the minimum conditions required for biological processes to persist, and the timescales over which isolated ecosystems can remain viable. This question connects directly to astrobiology. Jupiter's moon Europa possesses a global subsurface ocean beneath a crust of ice, maintained in liquid state by tidal heating from Jupiter's gravitational pull. Saturn's moon, Enceladus, vents plumes of water vapor and organic molecules from its subsurface ocean through cracks in its icy shell. Both moons present environments that bear striking structural resemblance to Antarctica's subglacial lakes, and the parallels are not lost on scientists working in either field. What is learned beneath Antarctic ice informs what instruments are designed to detect on other worlds. The protocols developed for clean drilling and contamination prevention in Antarctica serve as templates for future missions that may attempt to sample extraterrestrial subsurface environments. In this way, Antarctica functions as both a laboratory for Earth science and a proving ground for planetary exploration. Yet for all these advances, the dominant impression that emerges from contemporary Antarctic research is not one of mastery but of humility. Each new data set reveals not just answers, but the outlines of questions that had not previously been formulated. The subglacial landscape is more complex than early radar surveys suggested. The interactions between ice and ocean are more variable than models predicted. The biological systems beneath the ice are more widespread and more diverse than anyone expected. The continent does not yield its information in clean, satisfying packages. It yields it in fragments that must be assembled carefully, with full awareness that the picture they form is provisional and subject to revision as new fragments emerge. Antarctica seems almost designed to remind scientists that understanding is not a destination but a process, one that requires patience proportional to the timescales it seeks to comprehend. And those timescales, measured in millions and tens of millions of years, suggest that the process of understanding Antarctica has barely begun. Long before anyone set foot on Antarctic ice, the continent existed as an idea. Not a place with coordinates and coastlines, but a concept, a necessary shape in the architecture of a world that humans believed must be orderly. The ancient Greeks did not know Antarctica existed. They could not have known, but they believed in it, or rather they believed in the principle it represented, that the Earth required balance, that the known lands of the north must be mirrored by unknown lands in the south, that symmetry was not merely aesthetic but structural, woven into the fabric of how the world held itself together. This belief, born from philosophy rather than observation, would persist for more than 2,000 years, shaping maps, guiding expeditions, and filling the blank space at the bottom of the world with an imaginary continent that served human need long before the real one was discovered. The name they gave to this imagined landmass was Terra Australis Incognita, the unknown southern land. It appeared on maps as early as the 2nd century, when Ptolemy's geographical models suggested that the Indian Ocean was enclosed by land on its southern border. Medieval cartographers inherited this idea and elaborated on it, drawing vast southern continents that dwarfed the known land masses of the north. Some maps showed Terra Australis as fertile and populated, covered in forests and rivers, dotted with cities that existed only in the imagination of the mapmaker. Others left it deliberately vague, acknowledging ignorance while insisting on presence. The land had to be there. The world demanded it. And so it was drawn, again and again, century after century, a continent made of conviction rather than evidence. What is remarkable about this tradition is not that it was wrong, but that it was partly right. There is a continent at the bottom of the world. It is roughly where the ancient geographers placed it. It is enormous as they predicted. But it is nothing like what they imagined. The forests and rivers and cities they drew onto their maps do not exist on the surface. They exist, if at all, only in the geological record buried beneath ice that no ancient cartographer could have conceived of. The irony is precise. The imagined continent was lush and welcoming. The real continent is the most inhospitable place on Earth. And yet, beneath its ice, the remnants of a once living landscape lie preserved, closer in character to the green world the ancients imagined than to the white desert they would have found. This tension between imagination and reality has defined humanity's relationship with Antarctica from the beginning. When explorers finally reached the continent in the early 19th century, what they found was not the fertile land promised by centuries of speculation. It was ice, wind, cold beyond endurance, and an emptiness that resisted every attempt to domesticate or claim it. The heroic age of Antarctic exploration, spanning roughly from the 1890s to the 1920s, produced stories of astonishing endurance and terrible suffering, but it produced very little in the way of territorial conquest. Antarctica could be visited, it could be survived, barely, but it could not be owned in any meaningful sense. This reality eventually gave rise to something unprecedented in human political history. The Antarctic Treaty, Signed in 1959 by 12 nations, and since expanded to include dozens more, suspended all territorial claims on the continent and established Antarctica as a zone dedicated to peaceful purposes and scientific research. No military activity is permitted, no mineral extraction is allowed, no nuclear testing can occur. The treaty effectively removed an entire continent from the normal operations of sovereignty, commerce, and exploitation, placing it instead under a framework designed to protect its scientific value and environmental integrity. The treaty emerged in part from the geopolitical pressures of the Cold War, when both the United States and the Soviet Union recognized that competing for Antarctic territory could escalate tensions in a region where neither side had a clear advantage. But it also reflected a growing awareness that Antarctica was different, that its value lay not in what could be taken from it, but in what it could teach if left undisturbed. The International Geophysical Year of 1957 to 1958, a coordinated global effort to study Earth's physical properties, had demonstrated how much could be learned from Antarctic research when nations cooperated rather than competed. The treaty formalized that cooperation and gave it legal force. There is something quietly radical about the Antarctic Treaty. In a world where nearly every piece of land has been claimed, contested, exploited, and reshaped by human ambition, one continent remains set apart. Not because it is worthless, but because its worth is understood to lie in its intactness. This is a fragile arrangement. The treaty must be maintained through ongoing consensus among its signatories. Pressures to extract resources, particularly as other sources become scarce, could test its provisions. Climate change introduces uncertainties that the treaty's framers could not have anticipated. And yet for over 6 decades, the agreement has held, making Antarctica the closest thing the planet has to a commons preserved by collective restraint. The irony that shadows this achievement is that the forces most likely to undermine Antarctica's protection do not originate on the continent itself. They originate everywhere else. The burning of fossil fuels in distant cities warms oceans that thin Antarctic ice shelves from below. Agricultural and industrial emissions alter atmospheric composition in ways that change wind patterns over the Southern Ocean. Rising global temperatures threaten to destabilize ice sheets that have persisted for millions of years. Antarctica is protected from direct human exploitation by international law, but it is not protected from the indirect consequences of human activity occurring thousands of kilometers away. The treaty can prevent mining. It cannot prevent melting. This creates a situation of considerable tension. The most carefully protected place on Earth is also among the most vulnerable to changes originating beyond its borders. The scientific research that the treaty enables is producing increasingly urgent findings about the pace and scale of those changes, findings that carry implications not just for Antarctica but for coastlines, weather systems, and ecosystems worldwide. The continent that was once imagined as a counterbalance to the known world has become, in a very different sense, exactly that. Its ice sheets hold enough frozen water to raise global sea levels by more than 60 meters if fully melted. Its role in ocean circulation and atmospheric dynamics influences weather patterns across the planet. Its stability or instability will shape the physical geography of the Earth for centuries to come. The myths that once filled the blank space at the bottom of the world have largely faded. Lost civilizations, hidden cities, forgotten technologies. These stories persist in popular culture but carry no weight in scientific discourse. What has replaced them is something less dramatic but more consequential, a growing recognition that Antarctica's real significance lies not in what the imagination projects onto it, but in what its ice and rock and water actually contain. The continent does not need myths to be extraordinary. Its documented reality, forests buried under kilometers of ice, atmospheres sealed in frozen bubbles, lakes sealed in darkness for millions of years, microbial life persisting without sunlight, is more remarkable than any legend ever devised. And unlike the myths, the reality has consequences that extend far beyond the page or the screen, reaching into the physical future of a planet that has only recently begun to understand how much depends on what happens at its most remote and least understood frontier. There comes a moment in any long contemplation when the gaze turns back from the distance and settles on the present, not because the distance has been exhausted, but because the present has been changed by the looking. Antarctica does not release those who study it. It does not offer the satisfaction of a completed puzzle or the comfort of a story with a clear ending. Instead, it does something quieter and more persistent. It reshapes the frame through which the viewer sees everything else. The deep past, the buried landscapes, the sealed atmospheres, the silenced ecosystems, none of these remain safely in the past once they have been understood. They migrate forward, carried by implication, by analogy, by the simple recognition that the forces which shaped them are still at work, operating under different configurations but obeying the same indifferent physics. The continent is not a relic. This is perhaps the most important correction that prolonged attention to Antarctica demands. It is easy, even natural, to think of it as a museum, a frozen exhibit of what once was, sealed behind glass made of ice. But museums are static. Antarctica is not. Ice flows. It moves at rates imperceptible to the human eye but measurable by instruments, creeping toward the coast under its own weight, carrying with it everything trapped inside. Dust and ash and ancient air, delivering it to the sea in a slow, continuous exhalation that has been going on for millions of years. Subglacial water circulates through hidden channels, filling and draining lakes that no one has ever seen, lubricating the base of glaciers and influencing how fast they move. Geothermal heat rises from below, maintaining conditions at the ice-bedrock interface that are unlike anything on the surface. The continent breathes. Not in the way living things breathe, but in the way a system breathes, cycling energy and matter through pathways that connect the deep interior to the global ocean and atmosphere. This ongoing activity means that Antarctica's past is not merely recorded, it is expressed. The topography of buried mountains determines where ice thickens and where it thins. Ancient river valleys, carved when water flowed freely, now guide glaciers along paths that were established under entirely different climatic conditions. Sediment layers deposited tens of millions of years ago influence the friction between ice and bedrock, affecting flow rates that in turn affect how much ice reaches the sea. The past is embedded in the structure of the present, not as memory in the human sense, but as configuration, as the accumulated geometry of processes that never fully stopped, only changed form. This carries implications that extend well beyond the continent itself. Antarctica's ice shelves buttress glaciers that hold back vast reserves of land-based ice. When shelves thin or collapse, the glaciers behind them accelerate, delivering more ice to the ocean and contributing to sea level rise. This process is already underway in parts of West Antarctica, where warm ocean water is reaching beneath ice shelves and eroding them from below. The rate of change is not uniform. Some regions are relatively stable. Others are showing signs of acceleration that concern glaciologists studying the long-term trajectory of the ice sheet. The bedrock topography beneath these regions, mapped painstakingly by radar over decades, reveals why some areas are more vulnerable than others. Where the bed slopes downward toward the interior of the continent, retreat can become self-sustaining, a process known as marine ice sheet instability, in which the retreat of the grounding line exposes thicker ice to warm water, increasing the rate of melting and driving further retreat. The geological record shows that this process has occurred before. Sediment cores from beneath ice shelves and from the seafloor around Antarctica contain evidence of past episodes when ice sheets shrank significantly, sometimes losing large portions of their mass over periods that were geologically brief. These episodes corresponded to warm periods that were not dramatically warmer than the present, a detail that narrows the margin of comfort for anyone inclined to assume that current ice sheets are inherently stable. Stability, as Antarctica's own history demonstrates, is not a permanent condition. It is a balance maintained by forces that can shift, and the continent's deep record is filled with examples of balances that held for thousands of years before giving way. Yet the perspective that Antarctica offers is not solely one of warning, it is also one of context. The planet has moved through many states, from ice-free poles to glacial maxima that covered vast areas of the northern continents with sheets of ice kilometers thick. Each state was temporary. Each transition involved feedbacks and thresholds that played out over time, scales ranging from centuries to millions of years. Understanding these transitions does not predict the future with certainty, but it constrains the range of possibilities and identifies the mechanisms most likely to matter. Antarctica's archives, both in ice and in the sediments beneath, provide the empirical foundation for this understanding. Without them, climate science would be operating with far less data and far more speculation. There is also something to be said for the perspective that Antarctica imposes simply by existing. In a world saturated with noise, with information, with the relentless urgency of human affairs, Antarctica remains a place that operates on its own schedule. It does not hurry, does not respond to the news cycle or the political calendar. Its changes unfold across timescales that dwarf every institution, every civilization, every language that humans have ever produced. This is not indifference, it is proportion. The continent offers a measure of time that makes human activity visible in a different way, not as the centre of the story, but as one layer among many, forming now, influenced by what came before, influencing what comes after. The ice continues to fall, it compacts, it buries the present just as it buried the past. Somewhere on the interior plateau, snow that fell this year is beginning the long, slow compression that will, in a few hundred years, seal today's atmosphere into tiny bubbles, locking in the chemical signature of this particular moment in Earth's history. Future scientists, if they exist, may one day drill into that layer and read what we left behind. They will find carbon dioxide levels unlike anything in the previous 800,000 years of the record. They will find traces of industrial chemicals, microplastics, radioactive isotopes from nuclear testing. They will find the fingerprint of a species that altered the composition of its own atmosphere faster than any natural process recorded in the ice before it. What they will make of that fingerprint is not something Antarctica can tell us. The continent does not interpret. It does not judge. It records, with the same mechanical faithfulness it has applied to volcanic eruptions and orbital cycles, and the slow drift of continents across the face of the planet. It adds layer upon layer, pressing each one down with the weight of everything that follows, preserving it in darkness and cold and silence. And beneath it all, beneath the modern snow and the ancient ice and the buried mountains and the sealed lakes, the bedrock waits, patient, unmoved, carrying the memory of a greener world on its surface like a scar that the ice has kept from healing. The continent turns slowly beneath the sky, holding its past close, offering nothing freely, yielding only to those who approach with care and time and the willingness to listen to a story that has no ending, only depth, measured not in words but in the quiet accumulation of everything the world has chosen to forget and everything the ice has chosen to remember.